Welcome back. In this section, we'll be talking about the idea of functions and relations. First, beginning with the more general idea, a relation is just any set of ordered pairs. So we have some set X, which might be a set of numbers, not necessarily, and a set Y, again, it might be a set containing numbers, not necessarily. And we're taking ordered X and Y pairs. So some element from X and some element from Y. And that would be a relation. If you're thinking in terms of set X and set Y as being numbers, then anything that you might graph on an X and Y axis would be a relation. So for example, the graph of the equation of a circle, that would be an example of a relation. It's just a collection of X and Y points. So we can say a couple of things language-wise here, that if we have a pair of X and Y points, you could say that the X value relates to Y, or the Y value depends on X. That might be something that you could say, or that X maps to Y. Those are all sorts of ways that we express these X and Y pairs. Here's an example, though, of a relation where the sets X and Y, where they are not numbers. Here is X is the set of all the countries in the world, and Y is the set of all the cities in the world. And the relation that we're defining is that X relates to Y. In other words, we'll have an X and Y pair if city Y happens to be located in country X. So something like Canada, comma, Victoria, that would be a pair, because Canada is a country, Victoria is a city, and Victoria is located in Canada. So Canada, comma, Victoria, that would be a pair in our relation. Just like USA, comma, Seattle, that would be a pair as well, because USA is a country, Seattle is a city, and Seattle is a city which happens to be in the USA. However, Canada, Seattle, comma, Canada, that would not be a pair that's in our relation, because although Canada is something in the set X and Seattle is something in the set Y, it doesn't fit the requirement that the city happens to be located in that country. So one thing that you might notice about even just this relation is that it's possible to have the same X value corresponding with more than one Y value. So for example, although we have Canada, comma, Victoria is a point, we also have Canada, comma, Toronto would be a pair or a point in this relation, as would USA, comma, New York City. That would be another pair that we would have. So it's possible that you could have in a relation one X coordinate that has more than one Y coordinate that maps to it. And we can see, in fact, for this particular relation, there would be for Canada, comma, whatever the city is. There's lots of cities in Canada. So in fact, there's not just one or two points that have the same X value. There's lots of them. Now, if we want to restrict our idea to of a set of points to something where each X value only corresponds to one Y value, then we have something a little bit more special. And we'll see that in just a little bit. That special thing, of course, you'll remember from previous days, where each X corresponds to exactly one Y, that's a function. But whether we're talking about functions or relations, whenever we're talking about these pairs of points, we can express them in a bunch of different ways. One way might be if you have a limited number of pairs, you might list them as a set. So that's what I've done here. The curly brackets to give the notation of a set. So that's our collection of paired points. And there we go. We have our four pairs in this relation. 1, 1, negative 1, 1. 2, 4, and negative 2, 4. Another way that you could do the same thing is to show a mapping, and in a mapping that's just a visual representation. So here we have the collection of all of our input values, all of those X values, and here we have the collection of all of the Y values, the output values. And you can see that these are exactly the same points as we had in the previous example. So for example, 2 mapping to 4, so 2 comma 4. We also have negative 2 mapping to 4, so negative 2 comma 4. And the other 2 points you can also see shown with those arrows. This is sort of a nice way when you're first introducing the idea of a relation, that idea of thinking about some input value being transformed or mapped into some output value. And in fact, that's usually how we introduce the idea of a function as a machine that takes an input value and does something to it. So now to introduce the idea of a function formally, we've got 2 sets, and just so that we have sets with things in them, we're saying that they're non-empty sets. Again, for the most part, we're going to be interested in sets which are sets of numbers. So x and y are sets, typically would be real numbers or natural numbers or integers. But for the definition of a function, it's not really required. You could have x and y being sets of other things, sets of other kinds of objects. The idea here is that we have a relation, but now the restriction on a relation is every x in the first set will map to exactly one y in the second set. So in other words, every input maps up with exactly one output. If you're thinking in terms of those mapping diagrams, that would mean that for every input, there should be only one arrow coming out of it leading to an output. So something like 1 mapping to 2, that would be fine. You would see that in a function, but you wouldn't see 1 also mapping to some other value. That would mean that this is no longer a function, because now you have one x value mapping to more than one y value. A couple of other little things here. One is just as far as naming conventions go, since we're thinking about y as depending on the value of x, so that whatever the value of x is, that will tell you what the value of y will be that corresponds to it. So you would call y the dependent variable. It depends on whatever x is. And you would say that then x is the independent variable. X can take on whatever value it takes on, but whatever value you choose for x, the value for y will then depend on that. Sometimes you'll also call x the argument of the function, and that gets used in a bunch of places, like, for example, if you're talking about a square rooting function and you wanted to talk about what's inside the square root, you would say that that's the argument of the square root. And same thing with some other kinds of functions. The thing that's going into the function, that's the argument of the function. So most of the time, though, when we're talking about functions, we won't be listing them as pairs of points or drawing those little mapping diagrams. Normally, we write a function as an expression using variables. Normally, we would write it as f of x is equal to something involving x's. And so that gets us into the idea of our naming conventions. Normally what we'll do is we'll name a function with a single letter. So for example, you might call the single letter name for a function f. And to show that f is taking x values and giving you as an output a y value, you would write this, that y is equal to f of x. That's telling you that x is the input, or in other words, x is the independent variable, and that y will depend on whatever x is, so y is the dependent variable. So for something like this equation y is equal to 3x squared, it's possible that an equation might represent a function where one variable is a function of the other, but it might not represent a function in the other direction. So here we're interested in, is y a function of x? Is x a function of y? And it's possible that for some equations both might be true, that you might be able to think of y being a function of x and x also being a function of y. It's also true for some equations that neither would be true. So for this one, the question of is y a function of x, the question then is, for every x that we choose, do we get only one y value? And the answer to that is yes. If you select any x value, then 3x squared will only have one value. So that means that each x will correspond to exactly one y. And that's what we mean by something being a function. Every input leads you to exactly one output. And you can just imagine that here, that if I gave you a value for x, and I said, could you please calculate 3x squared, you're only going to have one answer for me for what is the value of 3x squared. So that's what I mean by select any x, and then 3x squared will only have one value. There'll only be one value you could find for what y would be. So for every x, you will get exactly one y, and that means that yes, y is a function of x. Now, on the other hand, if you wanted to switch it around and ask, is x a function of y, the answer for that is no. And so, for example, if you were to select a y value of 3, then this would mean that 3 should be equal to 3x squared, or in other words, 1 would be equal to x squared, which means that x is either the positive or the negative root of 1. In other words, we have one y value and it corresponds to more than one x value. So for one input y value, we don't get one output x value, we get two of them. This is why this would not be a function. Why, if you're thinking about y being the input and x being the output, this equation would no longer represent a function. So since one y corresponds to two x values, x is not a function of y. All right, just a few more things to talk about here. One being domain, codomain, and range. Domain, most of us will remember this. Domain is the set of all the possible input values that we can have for our function. The other two terms, a lot of times we'll get a little bit confused as to the distinction between them. So codomain and range are both referring to y values, but in a slightly different sense. So when I say the codomain for a function, the codomain is the set of all the possible output values. So you might say, here's a function going from this set of x values into this set of y values. So x would be our domain. Those are all of our possible input values, and y, that's our codomain. That's the possible y values. Now, the y values that you actually do get as your output values for your x, those are those images of x. Those are the output values that we would actually observe for each of those values in that set x. We would call all those output values that we would actually see, we call that the range. So the distinction between the codomain and the range is this. Suppose you're defining this function y equals 2x, and you're saying it's a function from the natural numbers to the natural numbers. So I'm specifying that the natural numbers then, that would be my domain, and the possible output values are going to be natural numbers too. That means that's my codomain. But that's not the list of all the y values that I'll actually see. When I say that my codomain is the natural numbers, I'm not saying that for my y values I will have a 1 and a 2 and a 3 and a 4 all as my possible output values. It's just that any output values I have will be inside this set. Now, if you're interested in what actually are the possible output values, then you're interested in the range of my function. And if you're looking at this function, you can see that whatever x value you put in, the y value gets calculated by taking that x value and multiplying by 2. In other words, the y values should always be even. So if you're thinking about what are the images of the x values, what y values would you actually see? Well, the images would be the even numbers, 2, 4, 6, 8, 10, and so on. So although I might specify in the beginning that we're taking natural numbers as our inputs and getting natural numbers as our output, in other words, natural numbers for the domain, natural numbers for the codomain, the values that we actually see for our output, the image values, the range, that set of the output values, is actually not the natural numbers itself. It's part of the natural numbers, 2, 4, 6, 8, and so on. So let's take a look here. We've got some sets that are listed here, sets of points. And the question that we want to know is which of these are relations that are also functions. All of these are relations because a relation is just any collection of pairs. If we happen to have that every input, every first coordinate matches up with exactly one second coordinate, so in other words, if every input has exactly one output, then we've got ourselves a relation that's also a function. So looking at the first one we have, you can see that the input values 1, 2, 5, 6, that they all show up exactly once. That means that the output value when x is 1, there's only one answer to that, it's a 3. The output value when x is 2, there's only one answer to that, it's a 6. And then same thing for the other 2 points. So for this is a function. And if we're thinking about our domain, that would be the set of all of our input values. So we have 1 and 2, and there's a 5, and there's a 6. And then when we think about our range here, the values that we actually see as our output values, there's a 3, there's a 6, there's a 10, and there's a 0. One thing just to mention as I'm writing this down, for set notation that we're using here, again, curly brackets are always used to contain a set. That's number one. And number two, inside a set, we only list individual numbers once. So if, let's say, we had an output value of 0 that showed up in another point, also another output value of 0, I wouldn't list 0 twice. I would only list 0 once in my range. The other part that's important to remember for sets is that in a set, the order that we list things doesn't matter. So for my range, I could have said it's the set 0, 3, 6, 10, or I could have said it's the set 10, 6, 0, 3, or whatever order I'd like to give them, and it really doesn't make any difference. It would still be considered the same set. Now, for the second example, we've got, if we're looking at our points here, we see there's 1 as an input value. It's got only one output value. 2 is an input. There's only one output. But for 3, we can see 3 shows up as an input value, and it has 2 different output values. So this is not a function. So it's not a function, and the reason why is because 3 maps to 2 different values. Finally, for the last one here, if we're looking at our points, you can see that there's an input value of 1 that gets used once, and 2 gets used once as input, so does 3, so does 4, so does 5. Every x coordinate shows up exactly once, so yes, this is a function. One thing that I know that people might say, they might say, well, hold on, there's this point here where the output value gets reused. 5 shows up as an output once, and then 5 shows up as an output again. But for something to be a function, there's no restrictions on how many times a y value gets reused. The only restriction is on how many times the input shows up, and every input can show up at most once. Every input has to have exactly one output that matches with it, so that means you can't have, for example, 3 being the input value twice, but you totally can have 5 being the output value twice. That doesn't prevent it from being a function. So would I say that this is a function? The answer would that be yes, it is a function. And if we're thinking about our domain here, the domain contains the set of all of our input values. There's a 2, there's a 3, there's a 4, there's a 5, there's a 1. And again, whatever order you list them, it doesn't matter. When it comes time to listing the values in my range, I'll list the values. I see I have an output value of 1, an output value of 5, another output value of 5, so I won't list it again, because in sets we only list things once. I have an output value of 2, and I have an output value of 7. So the things that are inside my range, the numbers 1, 5, 2, and 7. All right, one last little thing to work on here, which is the function going from the reals to the reals. That's what this little symbol that we have here, the little fancy letter R, that's the letter that we use to symbolize the set of real numbers. So f is a function going from the real numbers to the real numbers, and we have f of x defined as square root of x squared plus 1. So the first two parts are the easy parts to answer. The domain and the codomain, I told you already. In fact, I said it right at the very beginning where I said f is the function from R to R. When I say that, that's telling you what the domain is, the set of all real numbers, and the codomain, also the set of all real numbers. So this is telling us that we're going to take real numbers as our input values and that we'll get a real number as our output. Now, the question as to what is the range, this is something where we're going to need to be a little bit clever here, and I'm going to just write on the side. One thing that we might notice is that x squared that's inside of this has the smallest possible value that it can be would be 0. So this is one fact. X squared will always be 0 or larger. No matter what value you put in for x and square it, the smallest it could ever be would be 0. And that means that x squared plus 1 is always 1 or larger. Because, of course, if x squared, the smallest it could be is 0, then x squared plus 1, the smallest it could ever be is 1. And that means that the square root of x squared plus 1 is always square root of 1, which is 1, or larger. So when we're thinking about this function f of x, although the output will be real numbers, we're not going to see all the real numbers for our range. We're only going to see the values that are 1 or larger. So for this, I'm going to express my range in interval notation as the values from 1, including 1, and larger. And there we go. So for this function, my domain is all the real numbers, my codomain, all the real numbers, but my range, the numbers that are 1 or larger.